All right, today we're going to finish up with the linearization differentials. There's going to be a little bit of application. You can kind of see where they come into play and why they're useful. So, as a review, the big idea is find the tangent line and use it in place of the function. So, linearization was simply use the equation of the tangent line. If I can draw correctly. So we're still using our tangent line equation. Nothing's really different about it. The only difference is we're kind of putting it into a different context. So in this case, the estimation versus just, I know that I could find the value, but it might be easier to do it this way, and I might actually avoid some round off error if I do so. Differentials are focusing on the component change, aka we're looking at what's the rise. So remember, this is the same as dy dx, or dy equals f prime of dx. And its goal is, if I were to move by, again, let's say it's ticket prices. If we were to move the ticket price up $1, does that increase our profits? Does it decrease our profits? Things like that. So differentials, think about it. It's got the word different in it. It's looking at how much is it changing. Linearization, think about a tangent line. We have the word line in there. So linearization is using a tangent line to estimate an actual value, and a differential is using the derivative and how much you moved either left or right to estimate how much it changed up or down. So let's take a look at this. So pi over 2 is roughly 1.57. So what's cosine of, well, 1.56? So again, you can say, well, I could just plug in cosine of 1.56, which is true. You could do that. The thing is, though, cosine of 1.56 is going to be estimated. We're also going to be estimating here, but it's the difference between a trig estimation versus kind of an algebraic one, where there's a lot less room for error. Take into account if maybe it was cosine of x plus sine of x, and then you did cosine of x plus, or sorry, cosine of 1.56 plus sine of 1.56. Those two are going to be estimated when you do them individually, and then their sum is a sum of already estimated parts, which means you have error compiling on error. So this is a case where it might be a bit more useful. So remember, our tangent line equation is y equals f prime of a. And remember, a is what we're centering about. Times x minus a plus f of a. So we're going to center about 1.57. Specifically, we're going to center about pi over 2. So if y is cosine of x, then y prime will be negative sine of x. So when we're building our components, we have f of pi over 2. So cosine of pi over 2 is 0. And f prime of pi over 2. Sine of pi over 2 is 1, so negative sine of pi over 2 is going to be negative 1. So our equation is going to be, so the linearization remember, instead of writing y, we say L of x equals -1 times x minus pi over 2 plus 0. So -1 is our f prime of a, times x minus pi over 2 is our a value, plus f of a is 0. So simply put, for this one, L of x is -x plus pi over 2. So when we try and find cosine of 1.56, I'm just going to do what's L of 1.56. And that's going to give me -1.56 plus 1.57, which is going to be positive 0.01. So then what about cosine of 1.59? Same idea. Just going to use the linearization function we came up with. And so we'll get -1.59 plus 1.57 equals -0.02. Which, if you look to the right, which would be close to the 1.57, it is a negative value. And if you look to the left, which would be 1.56, it's about a positive value. Or it's a positive value. So it does work out. And again, you want to pick good points because... Let me do this one. What is cosine of 0.01? So 0.01 is about here. So it should be close to 1. But look what happens. If I do L of 0.01, I get -0.01 plus 1.57, which is 1.56. So this is why I say make sure that you pick points that make sense. Don't pick something that strays too far away, because if you do, you end up with something like this where your estimate is very far off because, well, cosine of anything can only fall between 1 and -1. So our linearization is only good close by to the points that we've picked. So don't stray too far from those points. Like I said, 1 or 2, and it also kind of depends on the slope. Because if the slope is shallower around it, that means that it's not going to be changing as much, which means your estimations might be better farther out. If the slope is very dramatic and it changes a lot, then you may want to be even more careful because because if you pick a point that's too far away and its slope is changing very fast, then there's a very strong possibility that you can mess something up when you do your estimation. So this is kind of an example of that. So this is the function, the square root of 1 plus x. And notice as you get further away from -1, the slope kind of levels out. So there's extreme differences at about 1. So I don't know about where this point would be. Maybe -3/4. Then here at 0. Notice how these tangent lines, so this has the steepest slope. Then this has the second steepest. And then here, this is the shallowest. And notice for a decent amount of values, to the left and to the right in this case, it's actually not straying too far. And that's because if we were to take the derivative of this, which would be 1 over 2 square roots of 1 plus x. So as x goes to infinity, y prime goes to 0, because this is going to be 1 over something really large, which is going to constantly get smaller and smaller. So as you go further out to the right, you're going to have better estimations of this. And so you could actually use this function to do some pretty decent estimations. So, like notice here, if I plugged in 4, I would get the square root of 5. So if you use this function, you could get a good approximation of the square root of 5. It might not be, again, it won't be exact, but you can get something pretty close. And again, you would be doing square root of 1 plus 4, because that's what the function is. So, just kind of in summary, accuracy is not a constant over the whole curve. If the curve is steeper, or where it's changing faster, the accuracy is a lot less. So, the shallower a curve, the better estimation you're going to have farther out. The steeper the curve, the worse estimation you're going to have farther out. So, again, if you go back to here, so even at 0, you don't even get out to -1 before you're pretty far off. And at 1, you're also pretty far off. But notice at 3, get to 2, you're still pretty good. So 1 would probably still be okay. And then as you look, though, to the right, at 4, you're still really close. As you would go further and further out, it would drift further away, but the accuracy would dissipate at a slower rate. So always, if you're planning for accuracy, stay close to a good point. So notice the reason these points were chosen. This one was chosen kind of as a different example, because if you do this one, you would get the square root. So again, if this is -3/4, you would end up taking the square root of 1/4, because you would plug in -3/4 here. So that's 1/2. If you plug in 0, you get the square root of 1. If you plug in 3, you get the square root of 4. So pick points that are close to the points you're trying to estimate. Like with the previous one, don't pick pi over 2 and then try and estimate 0. Trig functions are already kind of sporadic, so doing that is not going to help. So differential, the point of it is to, again, approximate the change. I'm not going to get the exact change when I do this, but I will get a very close change. Because if you want to actually estimate, you do the actual slope. You do y2 minus y1, and then look at the rate of change from there. That gives you the exact rate of change. But maybe you're just working with models. And by models, I mean like a modeling function. And so you want to just do quick tests. So instead of doing that, you just take the derivative of your modeling function and just go through it from there. So your delta y is going to be the exact one that I was talking about is here. So let's just kind of name some things out. So first thing you got to assume, y equals f of x is differentiable. If that doesn't happen, you're out of luck. So then the differential dx is independent from everything else. and then the differential dy is equal to f prime of a times dx. So notice here, you have dx, and that's the independent part, because when there's a small change in x, the corresponding change in the linearization is precisely dy. So what this means is you have to do a very small change to get exactly there, because remember, you're doing an estimate. Here's the exact, and here's the estimate. The change in the height, that's kind of like your linearization if you want to think about it that way. Because you notice here's the tangent at the point, then we're technically taking the linearized value at the point and figuring it out from there. Now the error in the differential is, so this is the actual minus the estimate. So our linearization at the point x is the same as the differential in y. So it's a kind of an interesting thing to see how these two relate together. So, for example, this is kind of just let me show you how these things happen. So, let's say you had a circle. And for example, maybe you're working in a factory and you're making pipes. So this might be the radius of one of those pipes. And you say, okay, well, it's got to be 10 inches across, or it's got to have a radius of 10 inches. And what happens to the error if you say are off by 1/10 of an inch? So that's your dr, this 0.1. So remember, the area would be pi r squared. So that means if we do the derivative of a with respect to r, pi is a constant, so we'll get 2 pi times r, because this would be pi times 2r, but just to make it easier to read. So that means dA is going to be equal to 2 pi r times the change in the radius. And we're going to use lowercase a as our particular radius here. So again, if you wanted to get the exact, you would need, so I'm just kind of making this note off to the side, the exact area, or the exact difference, is pi times the radius plus the change in x squared minus pi times the original radius squared. So that's the exact difference. This is the estimated difference. So this is kind of an interesting case. If we take the radii of all of these, and we want to find what's the differential estimate error, notice if the radius is 50 and we still have this rate of, or this being off by 0.1, the actual change, or the estimated change in the area, is this column, your dA. The exact change is delta A. That's what this triangle is. Remember from way back in the beginning of class, delta meant change. This is the exact change in this case. So here, regardless of what you make the radius, if the change increases by this, if you have this dr, which is how much the area, or not the area, sorry, how much the radius is extended, they have a consistent epsilon error. And the epsilon here is the differential estimate error. So that's kind of an interesting thing to keep in mind, that regardless, the ratio is practically the same. It's always 0.0314, which that should look familiar. Of course, if it was 3.14, that would be pi. So these are varying by about pi over 100, because pi over 10 would make it 0.314, pi over 100 would make it 0.0314, and so on. So your linearization error is very interesting with this example. And so that was exactly what I wrote. Which you notice, though, if you solved it, this is pi 2a, if you could factor out the pi. What would happen is, if this would become a squared plus 2a dr plus dr squared. So then this pi and the minus pi a squared would cancel. So you actually get this exact error. And so remember I said it was pi times 100. So the actual change minus this is just dr squared. So there's your delta A. And then if you subtracted that from the actual, which would be pi r squared, or sorry, dA, which is 2 pi r dr. dA would be 2 pi a times dr. Then notice here, this would cancel with this, and all you would be left with is pi times dr squared. So in this case, so with a circle, regardless of how large the change is, the differential estimate error is always going to be a factor of pi times the rate, or times the difference from the original squared. So if this was pi times, let's say you increased it by 1, the radius length by 1, then the error would be 3.14%. So exactly pi. So this is meant to illustrate that sometimes errors are consistent throughout. It's not always going to be the case, but a circle is a very interesting case where the differential estimate error is consistent throughout. It doesn't matter how big the radius is to start with. It's only going to depend on how much you increased the it's only going to change by how much you increase the radius by. So again, let's say you bump it up to 0.5. Remember, here's your estimate. Here's your actual. And 0.7854. This is all pi times 0.5 squared. And so the one above was pi times 0.1 squared. So it's consistent throughout. Now the error in your linearization is another one of the interesting things. So if y equals f of x is differentiable at the point A, and x changes from a to a plus delta x. So remember, this is your change in x, and it can be positive or negative, because it can be, if it's a positive change, you increase the value. If it's a negative change, you decrease the value. Then the change in y or the change delta y, it's hard to say change in or change in y, in f is given by an equation of this form. Delta y equals f prime of x, or sorry, f prime of a times delta x plus epsilon times delta x. So this is just another form of epsilon. So remember, epsilon originally was this, but it can also be written like this. The left one, the one that we use the most, is usually referred to like in coding as var epsilon, and this one is just epsilon. So you could also notice that this is delta x times f prime of x plus epsilon. So epsilon is still going to have a similar it's going to have a similar function as to when we did the not linearization, sorry, as to when we did the formal definition of a limit. It's still dealing with an error. The difference was the formal definition of a limit, it was an error bound. Now we're using it as an error. And so it makes sense that as epsilon goes to 0, or epsilon will go to 0 as delta x goes to 0. So the closer, which basically states the closer you are to the original x value, the less your error is going to be. So that's a nice thing and a nice sentiment to keep with you when you work with this. And it's really easy to figure that out. If you solve the equation for epsilon, you would have, well, first divide everything by delta x, so then you get delta y over delta x equals f prime of a plus epsilon. So then if you take the limit as delta x goes to 0, notice here, this was the same as your difference quotient, or that's what substitutes in here. And so as the rate of change between x goes to 0, like we said in the difference quotient, that takes the change in y to be the actual derivative at the point, which is why we say that the error will go to 0 as delta x goes to 0. So here's an actual example. So you have some accuracy requirements and you have an error. So how accurately must we manufacture the radius r if the volume must be within 3%? So this means you have a 3% plus or minus in the volume's error. So you have the volume can be plus or minus an epsilon as long as that epsilon is 3% within 3%. So if the volume is 100, we'll just use 100 for an easy example. 3% of 100 is just 3. So that means your volume of the container can be between 97 and, let's just say, 97 ounces. Let's just make it liquid for the sake of sanity. So let's say it's 97 ounces of liquid to 103. It means that anything in there is an acceptable value. Think about like plastic bottles. They may all come off of the manufacturing line and be really close, but maybe the plastic was denser in some areas than others. Maybe it was thinner, so some parts of the bottle may be not as either structurally stable, or it's not going to hold as much liquid because maybe the outer shell of it is a little bit thicker, thus meaning more liquid can't fit inside. So our specifications are as follows. So the radius has to be 2 inches. The height has to be 6 inches. And we can have a less than 0.5% error on this. So the 0.5% error is what we would refer to as a error ratio. So this is specifically for that's specifically for the height. So what this means is I need to have not the, now this is where you have to be careful. This is what I mean by you need to think about it as a ratio. So I need to have the change in the volume divided by the volume be less than 3%. The reason for that is if you're saying, well, I thought the volume had to be within that. It does. But go back and take a look at how we would talk about sorry. If you think about the way it was beforehand, the rate of change of the volume, if this was like dV dt, we don't need the volumes to be, or not the volumes, we don't need the rate of change, we need the change. That's kind of the difference between a differential and a derivative. A derivative is a rate of change, and it's kind of a ratio of change. Miles per hour, feet per second. When you only have a differential, you have just the change in the volume, the change in the miles, the change in the hours. So here, we need to have this ratio, because notice, technically what I would have is I'm saying that the volume has to be within 3%, so that means I can have an email. That's what I can have. I can have the rate of change for the volume be as, sorry, I'm getting tongue-tied. The change in the volume has to be less than 3% of the actual volume. And again, that's where that plus or minus kind of comes into play. I can go above or I can go beyond, but I can't, above and beyond are the same thing. I can go above by 3% and I go below by 3%, but I can't exceed down or up by 3%. So what we're going to do is we're going to use that the change in volume has to be less than 0.03 times the original volume. So one thing we're going to need is, what is dV? So that's kind of like step one, I should say. So if we do this, then dV is equal to, pi is a constant, so we're taking the differential of both sides. Remember, differential means kind of free game. You don't have to worry about what you're taking with respect to. So if you just think about r squared h as a product rule, so it would be the first, which would be r squared, times the derivative of h with respect to h would be 1. And then we include, think about it kind of like if you just went through and did the related rates way, where you took the derivative with respect to t, except just at the very end you dropped all the dt's. That would be how you would get this. And then plus, so then the second times the derivative of the first, So the derivative of r squared is 2r times dr. So if we do this, there's dv. So this is pi r squared h, or sorry, pi r squared dh. Pi r squared dh plus 2rh times dr. And this needs to be less than 0.03 pi r squared h. So far what I've done is, I'll kind of mark these in the cyan color. So we found the ratio, not ration, the ratio of change here. And then we found dv. And so now we need to look at, what do I actually not have in this equation? So there's pi r squared h, dh, and a dr. So I know, so I have r. So if I underline that, I have h, which I'll double underline. And I know, well, now this is what I need to start working with. So now here, this might be 2. I guess you could technically call it 3 because finding the ratio of change first. Now I need the ratio of change for the height. And again, the reason I know that is I was told that the 0.5% error is related to the height. Now maybe here I wasn't as clear when I wrote it, but I said the radius had to be 2 inches, the height had to be 6 inches, and have less than 0.5% error. That's not on both of them, that's specifically for the height. Let me just make that little note here. So let's find that ratio for the height. We'll set it up the same way as before but instead of dv, I'm going to have dh over h is less than 5%, which means dh has to be less than 0.05 times dh, or sorry, times just h. But keep in mind, we know our h, it's got to be 6. So dh has to be less than 0.05 times 6. So dh has to be less than 0.03. I can do math. Oh, whoops, this is 0.5%, so this is 0. 0.05. So no, I can't do math. I apologize. So this needs to be 0.03. So lo and behold, now we have DH. So notice we weren't given a specification for the radius. That was what we were asked to find. How accurately must we manufacture the radius R if the volume is to be within 3%? And we were given these specifications. That was also part of the reason why it was assumed that the 0.5% error was for the height, because the radius is accuracy, or the rate of change of the area. The change in the radius was what we were after. So now we're going to technically go for step 3, which is going to be solve for dr. So first thing I'm going to do is tell that to go away. Now you can do this one of two ways. You can go ahead and plug everything in and then solve, or I think it's better to just solve for dr and then plug everything in. So first thing we're going to do is subtract pi r squared dh from both sides, and that'll get me 2rh times dr is less than 0.03 pi r squared h minus pi r. Oh, this should be 2 pi rh. If you've been yelling at the screen, I finally fixed it. So minus pi r squared dh, and then divide both sides by 2 pi rh, and that gives us dr is less than let me try and kind of like separate things out a little bit. So that dr is less than 0.03 pi r squared h minus pi r squared dh divided by 2 pi rh. And if you want to, notice there's a common factor of pi times r in the numerator and the denominator. So to save space, if I factored that out and then canceled, I would get that dr is less than 0.03 rh minus r dh divided by 2h. Just double checking that all that's right. So pi r squared dh 2 pi rh. And then 0.03 pi r squared h. So after you plug everything in, so then dr is less than 0.03 times the radius of 2 times the height, which is 5, minus the radius of 2 times dh, which we said was 0.03, divided by 2 times the radius, or 2 times the height, which was 5, which gets you that dr is less than I'm going to go ahead and just do the math. It's going to be less than 1.25%. So as long as the radius is within 1.25% of 2 inches, then we have met our requirements. So the word problem answer would be the radius must be within 1.25% of 2 inches. So that tells you the accuracy requirement. So we know, so this is what we apply it to. And again, I keep saying "and again" a lot. I need to find a new catchphrase. With these type of problems, it's going to hurt me not to say it now that I'm painfully aware of it. You need to know what you're after. I need to know the change in the radius. I need to know how much it's allowed to change. So think of an application problem like I said, it could be bottles, it could be cans. Think about if these are rods that are connecting on like an aircraft or on a car, if they're part of like the framing. Think about how different the tolerance is going to have to be. If I tell you to build a plate for a rocket and it needs to be this thick, or if I tell you build a plate for a car hood and it needs to be this thick, the amount of error you're allowed in the thickness of the plate of the car is definitely going to be a lot more relaxed than it is on the thickness of the plate for the for the rocket. So these are some examples of where these can pop up. A lot of manufacturers will use these to actually figure out, okay, how much leeway do we have? Because if you need to be within 3% error, which 3% is pretty generous. Again, think about the difference between you're aiming for a volume of 100 cubic whatever, and you're allowed to be at 97 or 103. If we're talking about like a gas tank, which a cylindrical gas tank would be kind of weird, but if you're talking about that, okay, that's the difference between being able to hold 97 gallons versus 103. So there could be some major difference. If it's a vehicle, now again, a 100-gallon gas tank would be kind of astronomical for a car or something like that. But you think about planes, there's the gallon difference in, let's blow it up to be 1,000. Then 3% of 1,000 is 30. So you're allowed to have the gas tank be between 970 gallons and 1,030, which means if they overfill it, that could weigh the plane down differently, versus if the tank is too small, you may not have enough to actually make the trip. So these differentials are very important in, well, like it's called, it's error budgeting. It's how much error am I allowed? So then this is kind of the cheat sheet. And the left column is the exact change, or your true and the exact versus the estimate. So notice we kind of were using the relative change in the previous problem. It was how much change divided by the thing itself. So like we used in ours, we used dv and v and dh and h. So you have a lot that you can work with there. And of course, the percentage change is just multiply it by 100. So absolute change is f of the new value minus f of the original value. The estimate is f prime at the point, so the rate of change at the point, times how far away did you increase or decrease the x value. So that does it for chapter 3. We're going to move on to chapter 4 next, and that will begin the process of kind of diving a bit deeper in with the derivatives and dissecting functions a bit more and being able to tell more about them from the information we have. So I'll see y'all for that part.